All right, team, let's get going. Ready? Okay. So, as you guys are aware, today is the last full class time that we have together because the next time I would see you Thursday is the mentor day. So I'm not going to see you on Thursday. I will see you guys again on Friday, but it's only going to be for 45 minutes. So this is our last full session. Remember how we talked about last week that the plan was we get you guys going on ocean acidification. And with ocean acidification, what I want you guys to get done this week, let me just pull it up on the board so you guys can see it. Do you guys want the lights on or off now? Okay, would that be easier to see the projector? I'll do that. All right, Charlie. You've been voted out. All right. So for the ocean acidification essay, if you guys remember, I want us to get it to achieve first, and then we can work, or sorry, you guys will work on your own time to get it up to merit and excellence. So if you guys remember, we did a whole study plan last week. Yeah, the week before. Can't remember now. So the reason why I want us to focus on this internal instead of giving you guys more time for spec at the moment is because spec, everyone has essentially passed. So we do have those 3 credits in the bag. It's just a matter of polishing it up. So we decided that I will hunt you down during your study periods in the library and you will work on it then. Yeah? Okay, hunt you down. That means that I want to use today and Friday to make sure this ocean acidification is done, but just to the achieved level. So you don't have to worry about getting it up to the merit or excellence at this point. Again, we are aiming to get it just to the achieved level so we can ensure you guys have those 3 credits. Are we good so far? Okay. Next term, the plan is to focus on the externals. That means that with this internal, you guys are going to have to work on it outside of class time and to whatever kind of mark that you want. I will read it and give you feedback so that way you guys know if you're on track for an excellence or a merit, that sort of stuff. But remember, I'm only reading it once, so make sure whenever you hand it in to me that it is done. I don't want an incomplete draft. The deadline for that is going to be the end of the end of term 3. You have lots of time to do that. And then your corrections will be due before you guys go on study leave. Okay? So I know this one's far, far away in advance, but I do want to make sure you get the 3 credits first. The way we're going to make sure that we get these 3 credits is by completing this Google Doc this week, which is, let me zoom in so you guys can see it a bit better. Okay. Nope, too much. Okay. So this is a Google Doc, and what I've done is I've essentially taken all the achieve requirements and I formatted the requirement into a question, and you just type the answer to the question. So if you fill in this Google Doc, then you will have enough for achieved. Okay? So that's what we need to get done by this week. Are we good? Keep going? All right. If you guys want to get it to merit or excellence, so I'm only going to do the one kind of crash course lesson on ocean acidification today. So basically enough for you guys to understand stuff that you're reading to get kind of to the achieve level. If you want to aim for the merit or excellence level, I would suggest that you go to my Google site. And you can watch the videos from last year. So last year I did have more time and I did go through and do an individual lesson on different ideas. So these ones will be more in depth. So I recommend if you're aiming for merit or excellence on this essay to go through them so you have the information required to go to merit or excellence. Are we good so far? All right, let's crash course then for the achieve. So what we are thinking about in this topic is the process of ocean acidification, and I'm just trying to get this guy to focus, and I'm looking for my markers because I don't know where. There they are. Okay. And I gave you guys some pretty pictures too. So I'm doing a really abridged version because I want to give you guys time to work. So if it doesn't make sense, stop me. I can go in more depth. Just trying to see the notes that I wrote down earlier. There we go. Okay. Cool. Are you going to focus? Do I need the lights on for you to focus? There you go. Okay. So let's talk about chemical reactions as a basic point. So you guys are used to seeing chemical reactions and equations such as if we take magnesium and we add it to hydrochloric acid, we make magnesium chloride and hydrogen gas. And I'm just going to balance that and put the states in there. Let's try to get this guy to focus again. Okay. So you guys are used to seeing equations like that, and you're used to seeing things that only have the forward arrow. Are we good so far? All right. Some things we actually need to think about is that chemical reactions very rarely go to completion. Most chemical reactions reach something called equilibrium instead. So let me show you guys an example of that type of reaction. So let's say, for example, if I was going to make ammonia, I would need nitrogen, hydrogen, and that would make ammonia. Now I need to balance it. That's a 2, that's a 3. Yeah, okay. This is another equation that we've looked at. Now, the thing to remember about this equation is that not only does it go forward, it also goes backwards. So we can note that as having a forward and a backward arrow. The other way that you might see this being noted is like a half arrow going like that and a backward arrow going like that. So those are two ways you might see it being represented. What this tells you is that this reaction can go forward and backwards. Whereas if I only have this arrow going forward, that tells me the equation goes to completion. So it goes until it finishes up the reactants. Sorry, come on, focus again. Goes to completion, aka all reactants are used up. So we used up all the magnesium, or we used up all of the hydrochloric acid. Are we okay with that so far? Yeah? All right. Oh, come on. Okay. So when the forward and the reverse reaction are occurring at the same rate, we call that equilibrium. It has reached equilibrium. Now, something to remember about equilibrium is that it will look like the reaction has stopped, but it hasn't stopped. It's still going. You just can't visibly see a change. Are we okay with that so far? And I'll write that down. So no visible change. but there's still reactions going on. Q. That's a Q, guys. Sorry. All right. Can I give you an example of what I'm talking about? Hold on. I'm trying to do this really abridged. All right. Keep going. Okay. So let's think about a water bottle. And I have a couple that were in my room, but I think they've now since disappeared, thankfully. Okay. Here's my water bottle and some water. Yeah? Oi, boys in the back. Let's go wannabes. Want to listen? All right. So you guys see equilibrium all the time. You probably don't realize it. And I can see Mena has a water bottle right now. So if Mena has a water bottle and it's filled and the cap's on it and we leave it for a week and we come back, the water level is going to stay the same. Yep. Now, is there a chemical reaction, or I should say, want to be a chemical reaction? Is there a physical reaction occurring in that time frame, or is the water evaporating? It is. Yes. So what's happening here is the water is going from liquid to gas back to liquid. It's so weird. So in that bottle, there's going to be water in the gas form because there's air in there. There's also going to be water in the liquid form, which is sloshing around, which is what you can drink. Agreed? Okay. So if I close my container, there's water there that's in the liquid form that will evaporate to a gas. There's also water in there that's in the gas form right now that's going to condense down to a liquid. You don't see any observable change, so you don't see the water level increasing or decreasing because this forward and reverse reaction are occurring at the same rate. So the water level appears not to change. Does that make sense? Yeah. Yeah, hold on. Let me just pause the recording. All right. Are we okay with this idea before we move on? Ladies, are we okay with this idea? Why the water level doesn't change? If I took off the cap, then the water level would change because I can actually get some escaping and evaporating. And I'll talk about disrupting equilibrium. All right. We okay with this? Okay. Right. I'm going to be doing a little bit of jumping around. I'll come back to this because I need to talk about disrupting the equilibrium. So we are going to be talking about in our next topic something called ocean acidification. So some things to keep in mind is we have acids and we have acids of different strengths. We have some really strong acids that are very damaging, like hydrochloric, which you would not want to drink. We also have some really weak acids that we can eat and drink. Once this decides to focus again, I'm just going to keep writing and hope it focuses. There we go. All right. We have some strong acids like hydrochloric acid. We also have some weak acids such as ethanoic acid, which is your vinegar. Are we okay with that so far? So when you mix these acids into water, they disassociate, they break apart, and they release the hydrogen ion. The hydrogen ion is what we need for something to be acidic. So when we mix hydrochloric acid into water, it will dissolve like that, and it releases that hydrogen ion. I need to buy a new document camera. I'm getting fed up with this guy. And that hydrogen ion is what's caused something to be acidic. Okay, so far. All right. A weaker acid, such as ethanoic acid, doesn't fully dissociate. It goes and it reaches equilibrium and it does that forward backwards thing. So it releases the hydrogen ion and it forms a salt as a byproduct, like that. So you see how this one has a forward-backwards arrow and this one just has the forward arrow. So this one, 100% will dissociate and form the hydrogen ion. This one, only about 1% will dissociate. So that's why it's a really weak acid. This is a weak one. This is a strong one. So when this guy is at equilibrium, most of it will be ethanoic acid, and then a small amount of it will be hydrogen ions and the salt. Are we okay with that so far? There's strong acids and there's weak acids. The acid that I want you guys to think about for ocean acidification is carbonic acid. So let me get another color. Now there's lots of parts of this equation, but I'll just do the first kind of parts and then we'll talk about the other further parts. So the first thing about ocean acidification is that it does relate, come on. In the ocean, what we're actually thinking about is carbonic acid, and carbonic acid comes from carbon dioxide. So what happens is the carbon dioxide in the air mixes with the water. It reaches some sort of equilibrium, so it's reversible. And what it forms is carbonic acid. What are we? Oh, this is an L, liquid. I don't know why, but I was taught to do my liquids as like cursive instead of lines for this. That's liquid. Sorry, guys. Thank you for asking that. Aqueous. All right. So here's our carbon dioxide in the air. It's mixed with the ocean water. It's formed what we call bicarbonate. And it forms the hydrogen ion, which is the acid. Are we okay? Okay. Keep going. Okay. Now, there's another part in this equation that also goes forward and backwards. Now, we have, in this case, the carbonate ion and the hydrogen ions. So that's the full equation there. There we go. So this is the full equation for ocean acidification that we're thinking about. So what happens when we're looking at this is we have carbon dioxide. It mixes with the water. And in order to neutralize those hydrogen ions, we have something called carbonate. And so it helps get rid of the acidy bits. That's my carbonate. Oops. That one's an L. Do you want me just to make it look like an L? All right, are we okay so far? What are we not sure about? Last one, CO3, the 3 is small, superscript 2 minus, and then aqueous, and that's known as carbonate. All right, we okay? Can I keep going? Okay. So this section here is known as our ocean buffer. All right, keep going. So the buffer is supposed to maintain the pH. Do you guys remember what pH is referring to? Acidity and basic. So remember, it goes from 0 to 14. So the ocean has a pH, I think, of like 8.4, and we want to maintain that. So what this buffer does is that if there's too much acid, it goes to the left and neutralizes it. If there's too much base, it goes to the right and neutralizes it. So the whole idea is that the ocean maintains its pH with this ocean buffer. Now, what you guys are going to be researching is the fact that this buffer is being pushed to its capacity. So it's being pushed to its limit, and now we are running out of what we can neutralize. And so because we run out, we then have the ocean becoming more and more acidic. So the buffer cannot protect us anymore. Are we good with that? Okay. So, trying to see if I want to start showing you guys this. What I want to show. Okay. I don't want to say that. Okay. So we have to think about why is this happening, and we need to think about equilibrium and how it's pushing the various equations. So if we go back to our previous example, this one's a lot simpler to think about because less steps. There are 3 different ways you can affect equilibrium. The first way you can affect equilibrium is by changing concentrations of stuff. So step 1, we change concentration. So step 1, we change the concentration. So basically the idea is, if I change the concentration of the different components in the equation, I can force the reaction to go forward or backwards. Gentlemen. All right. So if I increase the products, I force my reaction to go forward because I want to use up the products. Are you okay with that? If I increase the reactants, I force the reaction to go backwards to use up the reactants and make more product. If I remove the reactants, I force it to go backwards to replace what was lost. If I remove the product, I force it to go forward to, again, replace what is lost. So that's the first thing we think about, is how does changing the concentration affect the equilibrium? Does it push it forward or does it push it backwards? So when we're thinking about ocean acidification, one of the things we're thinking about is the fact that our carbon dioxide levels in the atmosphere is increasing. We have more and more carbon dioxide in our air right now. So that's going to force it to go forward and thus promoting that ocean acidification. So that's one factor. Are we okay with that? Okay. Second factor is the pressure. So with pressure, if I increase it, we're going to go to the side with fewer gas molecules. And if we decrease the pressure, we go to the side with more gas particles. Now, this one isn't going to be as crucial for this example, and I'll explain why in a moment. But I just want to talk about what happens with pressure. So when I look at this equation up here, this has 4 moles of gas. So we have 3 from the hydrogen, 1 from the nitrogen, and this one has 2 moles of gas from the ammonia. That's 4, and that's 2. Do you want me to backtrack? You're okay. I just added these numbers together. 1 plus 3. And these are all gas. So if I increase the pressure, I want to go to the side with fewer molecules of gas. So that forces me to go forward because this only has 2 and that one has 4. If I decrease the pressure, then I want to go to the side with more gas molecules. This one has 2, that one has 4. It goes that way. So that's something to keep in mind. Doesn't really matter with the ocean acidification because you cannot change the pressure of Earth. So just pointing it out there, but we can't like encompass our planet and like increase the pressure of the planet or like decrease the pressure of the planet. So that's not a factor that you have to worry about. Are we okay so far? Yes, sorry. All right, third one is temperature. All right, third one is temperature. Now with temperature, I like to think of it as the same way as the concentration, except with the with putting in the energy in there. So if you guys remember, there's endothermic and exothermic. Exothermic releases heat energy, endothermic absorbs heat energy. So in this case, this is an exothermic reaction. It releases energy. So it releases 92 kilojoules. I'm running out of space per mole. So the forward is exothermic and the reverse is endothermic. So if I alter the temperature of this reaction, again, I can force the reaction to go forward or backwards. If I make this reaction colder, did I write that? I put it in the wrong spot. Sorry, guys. That's endo. That's exo. Sorry, I didn't realize the arrows were the other way around. All right. So if I make the reaction colder, I promote the forward reaction. So that way I release heat energy and I warm it up. If I add heat energy, I want to take it away. So I promote the reverse reaction, which is endothermic. Yeah. Are we okay with that so far? Yes. All right. So with the ocean acidification, just FYI, the forward reaction is exothermic, the dissolving of carbon dioxide into water, and then the reverse reaction is endothermic. And that's going to be important with what I talk about next. All right, keep going. Yes, no? I'm trying to do this quickly so you guys can move on. Okay. So, I was going to come back. Some things we got to think about with ocean acidification is that it's a really, really complex problem. So that's why I like to give you guys these bullet points. These bullet points here is what you need to be thinking about if you want to get this up to the merit or excellence level. So thinking about the multiple layers of this problem. The first thing that I want to say is that ocean acidification has been good for slowing climate change because with ocean acidification, the water absorbs the carbon dioxide and we have less carbon dioxide in the air, which is good. So it's kind of like a double-edged sword. It helps with the carbon dioxide levels, but now our oceans are being more acidic. Now, initially, the scientists were like, that is great. It's going to slow down climate change. And they weren't worried about ocean acidification. The reason why they weren't worried about it was because they thought there was enough carbonate in the ocean to neutralize the acid that was going to be forming. And that carbonate comes from, showing you guys lots of pictures. the weathering of the limestone. So we have rocks that have calcium carbonate, and then when they break down, they get mixed into the ocean. So we thought it's going to be fine, there's enough carbonate. Bad news, this is not happening fast enough for how quickly the ocean's becoming acidic. Okay? So that's the first thing that you got to keep in mind. So that's up to that bullet point. The other thing to keep in mind is that the temperature of the Earth is rising. So this is a double-edged sword. So the temperature of the Earth rising is good for ocean acidification because less carbon dioxide can dissolve into water. So it's harder to get the carbon dioxide to mix in the water because the forward is an exothermic reaction and we already have too much heat energy. So it's not going to do that. So that's the good news. Climate change is slowing down ocean acidification. The bad news is that this is a positive feedback loop. So if the ocean's not absorbing the carbon dioxide, more and more carbon dioxide gets into the air and the temperature keeps going higher and higher, and more carbon dioxide is not going to be going into the ocean. So it's a positive feedback loop. And did I write that down there? Increasing temperature, slowing down. Oh, yeah, it's a positive feedback loop. It's not good. Yeah. So it's not absorbing the carbon dioxide in the air anymore. More carbon dioxide in the air means there's more greenhouse effect. More greenhouse effect means temperature keeps going up. Less carbon dioxide is being absorbed and cycles. So, and the thing is, with the increase in temperature of the atmosphere, that's not a good thing either because then the ice caps melt. And when the ice caps melt, we dilute the ocean, so the ocean's less concentrated, and we also dilute the buffer. And when we dilute the buffer does not work as well. So again, we're not preventing ocean acidification as well. So you see, it's a really complicated problem. Yeah? And if you want that merit or excellence, you need to be able to kind of construct your answer to balance that difficulty in this problem. Okay? So some things that I also want you guys to think about is the relation to the carbon cycle. So carbon we can find in all of our biospheres. We can find it in the atmosphere as carbon dioxide. We can find it in the biosphere because all living things are made up of carbon. We can find it in the geosphere because carbon is mixed into the rocks, such as calcium carbonate, which is one of our rocks. And then carbon also is in the ocean because it mixes and becomes the carbonic acid. So carbon's everywhere in this cycle. Now, this was a really delicate balance for billions of years. And then, surprise, surprise, humans ruined it because we started burning things. And by burning things, we increased the carbon dioxide in the air. So we disrupted this beautiful balance that has taken billions of years to establish. Okay? So, yeah, we're terrible. So the thing to keep in mind is that we used to not have a problem with this because all of that carbon was locked into the solid state as stuff like fossil fuels. So it wasn't contributing to this problem. But the moment we burnt it, we now have it in our problem. Great job, humans. We messed up bad. All right, so this is just a picture of the carbon cycle. I would want you guys to reference the carbon cycle if you're aiming for merit or excellence. This is just another picture. I liked both of them because this one shows the complexity of all the different parts of the carbon cycle. This one here, though, includes the equations, which I think is useful. That's why I've included both. The other thing that you guys have on your sheets is this one here. And this one here just shows the concentrations of the different components based off of the pH. So with our pH of the ocean originally, it was supposed to be, a set amount of carbon dioxide, carbonate, and bicarbonate ions. And that was the balance. And it's really important to have these carbonate ions because shellfish and things need them. So we need this to build shells. Yeah. Bad news is that when we go lower and lower in the pH scale for the ocean, we have a drop in the carbonate. And the ocean animals that need it cannot use bicarbonate. So they can't use this one as a replacement. So bye-bye shells. So you can see here that as the ocean becomes more and more acidic, we're going to lose our carbonate ions. Okay? That's all right. So just so you guys are aware, on the student instruction sheet, there is links to various sources that you guys can use as a starting point, but you are welcome to find your own. And there's lots of different things in here to help you learn about what ocean acidification is, the carbon cycle, this impact on sea life. You got a lot of choices there. Like I said, I just want you guys to fill in just the Achieve Google Doc for this week. So answering these questions, make sure you have a reference list as well. And if you do that, that will be enough for the Achieved, with what we want to do at this point. Here is the success criteria. So what we're aiming for is to get all the Achieve stuff done before the end of term. Then you guys can work over the school holidays and a next term, that's misspelled apparently, on looking at the stuff for the merit and the excellence requirements. That's going to require more reading and research. Okay? Cool. I think that's it. And then when you guys are trying for the merit and excellence, there's a report document for you to write in. Okay? Cool. All right. Questions, concerns, comments? No? All right. Use the rest of the class time. You have about a half hour. Answer the Achieve document. Get that done and dusted. And then you'll have 3 credits in the bag.